Hello, everybody. My name is Dr. Jagabir Ningthoujam. I will be presenting the results of a pilot study that investigates the feasibility of using borehole density, sonic, and neutron logs as possible porosity indicators for mapping regional porosity variation in Silurian Lockport group and Selena group A1 carbonate unit in southern Ontario. In the past, Paleozoic strata in southern Ontario have been an important source of hydrocarbons. However, the current drivers for this project are our interest in these strata for hydrogeological mapping, potential site for hydrocarbon, CO2, and hydrogen fuel storage, and possible site for spent nuclear waste disposal. As I mentioned at the beginning, the objectives of this project are to investigate the reliability of using density, neutron, and sonic logs as possible porosity indicators, and this was carried out by comparing the density-derived, sonic-derived, and neutron porosity values with corresponding core porosity values for the same depth intervals. Before we dive into the details of the project, I would like to briefly highlight the geological background of the strata of interest. The studied stratigraphic interval straddles two Paleozoic sedimentary basins, the Michigan Basin and the Appalachian Basin. Deposition of the Lockport and Selena groups strata occurred during the Silurian period, in which the strata was largely covered by shallow subtropical epicontinental seas. The Lockport group comprises a stack of shallowing upward dolostone succession, which is then disconformably overlain by Selena group comprising a succession of microbial carbonates and mixed evaporites and shales. The data set for this study comprises 67 LAS files converted from analog geophysical logs of 33 petroleum industry wells and core porosity data for 27 petroleum wells. Since we're using very old data set, several challenges were encountered, including number one, unavailability of various key geophysical logs, number two, data conversion issues, and number three, limited stratigraphic extent of the core data. Now let's take a look at the results. Bulk density and its derived porosity show strong negative and positive correlation with corresponding core porosity values indicated by R-square of 0.587 and 0.589 respectively. On the other hand, sonic log and its derived porosity values show weak positive correlation with corresponding core porosity indicated by R-squares of 0.1738. Lastly, neutron porosity showed the weakest positive correlation with corresponding core porosity values indicated by R-square of 0.0574. So if they are all measuring porosity, why is there a difference in the derived porosity readings of these three log types? This can be attributed to the interaction between the logging tools and the formation that is being measured. Density log uses gamma ray to measure the bulk density, which is the density of the entire formation, solid plus fluid parts. Accordingly, its derived porosity reflects all the pore spaces in the formation and does provide a close approximation of the true porosity. Sonic log measures the shortest time required for a P sound wave to travel through 1 foot of a formation, which corresponds to a route in the borehole wall free of fractures and vugs. Therefore, porosity derived from sonic log fails to account for secondary porosity. Neutron log measures hydrogen concentration in a formation as a proxy for porosity. However, it fails to account for formation-related complexities like gas effect, chloride effect, and shale effect that can over or underestimate formation porosity. However, sonic and neutron logs can be combined with density logs to obtain meaningful porosity-related results. Sonic porosity, when subtracted from density porosity, can give us a good estimate of secondary porosity in a formation. Neutron porosity, when combined with density porosity, can be used to identify gas-bearing zone by looking for neutron density crossovers. We can then calculate the formation porosity of the gas-bearing zone by using this equation. Finally, here's a quick recap of the study. Density porosity shows the strongest positive correlation with the corresponding core porosity of the formation. Therefore, it is the most reliable porosity indicator. Sonic porosity and neutron porosity show weak and very weak positive correlation respectively with the corresponding core porosity of the formation. Therefore, they're less reliable. Sonic porosity can be subtracted from density porosity to determine the secondary porosity, and neutron porosity can be used in combination with density porosity to detect gas-bearing zones. And with that, I would like to thank everybody for listening and look forward to answering your questions.